Hello and welcome to Automation at Large, managing Ansible Tower on a massive scale. I'm Brant Evans and I'll be presenting today with Nick Autry. I'm a senior cloud architect with Red Hat Consulting. I've been with Red Hat for about 6 years, and when I'm not working with customers, I enjoy working on model railroads, playing disc golf with my son, and of course playing video games. And lately I've been doing some Pokemon Go.
And I'm Nick Autry. I'm a senior consultant with Red Hat. And when I'm not out helping customers with their Ansible automation, I can be found fishing or playing the newest board game or cooking dinner and trying to know new cuisines. So let's start this off. We're going to be discussing a real-world example of when Ansible Tower experiences large-scale performance issues. We will then deep dive into the underlying causes and the lessons learned. In our example here, this client had a massive Ansible Tower setup, including half a dozen clusters with varying amounts of nodes, all running on top of OpenShift. These clusters each manage tens to hundreds of thousands of endpoints, with thousands of jobs run a day. But after a few months, some of the Ansible Tower clusters started experiencing various performance issues, from an unresponsive web UI to the inability to run jobs and other random errors. These clusters became almost unusable at times. Due to this, hundreds of users were affected and unable to consistently run automation. What we will go over next is the issues we found and ways to solve them.
All right, so let's start by talking about the types of workloads. And these are workloads that impact the controller node, not necessarily the managed node that the job is running against. In our first example here, we have an example of a CPU-intensive task. This task is using a filter plugin, and filter plugins always run on the control node. By itself, this is a pretty innocent task, but when we're running this type of task against hundreds or thousands of nodes at the same time, we may easily oversaturate the CPU resources on the control node as they calculate the password hash. Similarly, we can have memory-intensive tasks. And again, this example looks pretty innocent. We're running a SQL query against a Postgres database. The query is running on the managed node, but the data for that query is being stored in a variable called all-data. That variable and the data in it gets transferred back to the control node. And when we're running at large scale, that can have a huge memory impact on the control node. We can have a task that combines the CPU and memory intensive type tasks, as in this example where we're using JSON query filter plugin that's going to use a lot of CPU resources on the control node, and the resulting data set is being stored in a new variable called real data, again, that's going to consume lots of memory on the control node. You can also have network-intensive tasks, such as this copy task that is copying a file from the control node to the managed node. And again, running this against one or two managed nodes, not really an issue. But when we scale this up and we're running against hundreds or thousands of nodes at the same time, this can saturate the network of the control node. Now, these types of tasks are necessary and needed, but we need to watch for them when we're creating the automation, so that we can plan to mitigate those tasks and the impacts that they can have on the control node. We're going to talk about some ways that these types of tasks can be mitigated.
So running a large amount of concurrent jobs, or even just a few long-running jobs, can affect the performance of Ansible Tower, especially if you're accidentally doing some of the things that Brant just discussed. So in this section, we will discuss some of the ways to mitigate this issue. In Ansible, parallelism is achieved by utilizing forks. When a certain number of forks is set, Ansible Tower will run each task in a job against that many number of hosts at the same time. This is especially useful when a job runs against a large number of hosts, like in the thousands, allowing you to run against a significant number of them simultaneously and generally reducing the overall runtime. For example, if you run against 100 hosts without specifying the forks, it will default to just 5 forks, which means Ansible will only be ran against 5 hosts at a time. But if the forks is set to 100, then Ansible will run against all 100 hosts simultaneously, which will greatly reduce the runtime. But while forks can improve the efficiency of a job run, they can also overwork the cluster if used incorrectly. Each instance within the cluster has a certain amount of available forks based on its underlying CPU and RAM. You can see here on this page that's from the instance groups within Tower that each instance is listed, and there's a number for the forks as well as a slider that adjusts it, and that's based totally off of the CPU and RAM available to that instance. If a job is using most or all of the available forks, it will prevent any other jobs from being run on that instance until it is completed. So for long-running jobs, over-allocating forks can result in other jobs getting stuck in a pending state for up to hours. So you have to make sure you use forks responsibly. While forks let you run against more hosts at the same time, slicing allows you to run on multiple Ansible Tower nodes at the same time. This results in a distributed load that helps prevent a single node from being overworked and running out of capacity. When slicing is set, Ansible Tower will break the job template up into multiple job templates within a workflow, as seen in the image here. Slicing is set within the template itself within Tower. Slicing can reduce the amount of stress on your nodes, as well as provide a significant performance boost. Slicing will automatically break up your job templates, but you can do it manually as well to lead to performance gains. By creating smaller, more concise playbooks that have their own templates, you can run them in a workflow with some of them running at the same time. This will allow for your jobs to run faster and give more flexibility with running certain tasks in parallel. So you could have some templates and playbooks that can run at the same time, and then they can converge back into one when you have a dependency that needs to be met. Failing to break up these large playbooks can result in long-running jobs that can hog the cluster's resources and ultimately bog them down. All of the suggestions I just gave above mainly relate to the Ansible Tower UI, but there are also changes that can be made at the configuration level. The ansible.cfg file, or Ansible config, contains various settings for Ansible and can be leveraged to optimize performance. You will put an Ansible CFG file in the top level of your project that Tower is running from, and Tower will automatically pick that up and apply the settings to the Ansible it's running. We've already discussed setting forks in the UI, but the default number can also be configured here, as seen. To help determine which tasks are more demanding or causing a bottleneck, the profile tasks callback can be enabled, giving you information about how long each task takes to complete. This will help you see what's causing everything to be slow and where you need to focus on improving the performance of your Ansible. Enabling pipelining will also improve performance by reducing the number of SSH connections that Ansible opens, while making use of the various timeout options can help you meet specific needs. It is important to be aware of the Ansible CFG files in the projects since they have settings that contradict what is configured in the UI, especially relating to forks. Settings in the UI will always take precedence over those in the Ansible config. So it's important to make sure that you know what the settings are in the UI as well, and don't just rely on the Ansible config settings.
All right, now let's talk about running Tower in a containerized environment like OpenShift. Here we have an architecture of an OpenShift cluster with application nodes where we're running on a physical server with 8 CPU cores, but there are 32 virtual CPUs configured in the hypervisor layer. This results in a 4-to-1 overcommit of virtual CPUs to physical CPUs. This causes resource contention within OpenShift and the hypervisor when allocating CPU resources and trying to run the workloads. Ideally, for OpenShift, we want a 1-to-1 relationship of virtual CPUs to physical CPUs. In addition, at the OpenShift layer, we need to look at what else is running on the application nodes. In the first application node example, we have a database pod and a Tower pod running on that application node. Although this may be fine, depending on the workload of the Tower pod or the workload of the database pod, they may be conflicting and trying to consume more resources than are available, thus impacting one another. Similarly, we need to look at application nodes like the second and third application node where we have a Tower pod and another application pod running on that node, as there may be contention for resources between the pods and impact one or both applications' performance. Okay. Finally, in application node 5, we can see, although it has more virtual CPUs, we have 2 Tower pods and an application X pod. So not only could Tower be competing with itself in this case, but it can be competing with application X and causing performance issues for Tower or for application X. Okay. When Tower is running in OpenShift, it runs in a pod with 4 containers. The most important container is the task container that is actually executing the jobs. By default, the task container is guaranteed 1,500 millicores and 2 gigs of memory. This is set by the task CPU request and task mem request in the Ansible inventory that is used during the Tower installation. By increasing these values, you directly impact the guaranteed CPU and memory resources that are allocated to the Tower pod, thus impacting the number of forks that are available for that Tower instance to use when you look at the instance group slider, as Nick showed earlier. By default, Tower requires 3 CPU cores and 6 gigs of memory for each pod that is being run.
Even when utilizing the techniques that Brant and I already discussed, monitoring your cluster is important in order to ensure the health and performance of Ansible Tower. Ansible Tower comes with built-in metrics to allow for easy monitoring. Multiple endpoints exist for the API which provide important data about the health of the cluster. The most important and useful one being the API v2 metrics endpoint. Tons of information including job run statistics, resource quantities, and CPU, memory, and capacity data can be obtained by querying this endpoint. Other helpful endpoints include the API v2 ping and API v2 instance groups. These contain similar information to the metrics, but they're more specific to exactly what you're looking for. And these metrics endpoints are good by themselves, but they become even more useful when combined with external monitoring tools. Prometheus, for example, can be configured to scrape data from Ansible Tower and organize it in one place. Grafana can then use that data and visualize it in the form of graphs for easy interpretation. Both tools allow for some degree of alerting to notify admins when something appears to be wrong with this cluster. Actively monitoring Ansible Tower is necessary for both presenting and resolving potential performance issues. As consultants, Brant and I often set this up for customers to help notify them and help them monitor that something is going to happen or break in the tower before it actually does, so we can prevent production outages. And now that we've talked about Prometheus, we can touch upon using the Prometheus node exporter to gather lower level metrics. Node exporter grants the ability to monitor data from the OS and OpenShift if applicable, to allow for a more holistic view of the health of your Ansible Tower. Since performance issues can be caused by configuration of the underlying infrastructure, it's important to keep an eye on these type of metrics. So by using Node Exporter, you can get more information about the CPU, what the file system looks like, how the memory is performing, and disk stats as well. And now that we've talked about active monitoring, we can touch upon exporting logs and trying to figure out what happened after something's gone wrong. Ansible Tower has native capabilities to allow for integration with external logging aggregators like Splunk or Elasticsearch. Exporting logs allows for keeping the database slim as well as provides an easier way to investigate performance issues. Normally, Tower keeps all the logs in its own database, so if there are a lot of logs that are built up and they're not cleaned up, it can really bog down Tower's database. As well as Tower allows for searching, but it's not as easy as using an external tool, and you can't really pinpoint as well. So external tools have easy-to-use interfaces and search capabilities that, combined with graphical dashboards, allow for a user-friendly way to pinpoint errors in logs.
All right, now let's talk about some of the upcoming features of Ansible Automation Platform 2 that will help continue to scale Ansible Tower to larger and larger environments. The first thing is that with Ansible Automation Platform 2, the control plane has been separated from the execution plane. This means that the job execution of running playbooks against the managed nodes will not have an impact on the UI as users are interacting with Tower. In addition, container groups have been introduced, which are similar to instance groups, but allow automation to be executed against namespaces in an OpenShift cluster. This allows for finer-grained management of resources at the OpenShift level, and for such things as having a namespace that is configured to CPU-intensive workloads, or a namespace that is configured to memory-intensive workloads, or to have namespaces configured for different groups so that one group's automation does not impact the running of automation from a second group. And lastly, we have execution environments. These replace the Python virtual environments that have been in previous versions that we've had to keep in sync across all of the Tower nodes. Execution environments are containers that have all of the components necessary for running the automation. So we may have execution environments that are built for network automation or Windows automation or Linux automation. And by having them be containers, they become more easily manageable and able to consume, and we don't have to worry about keeping them all in sync across all of the Tower nodes like we've had to with Python virtual environments. We thank you for attending today's presentation on running Ansible Tower at massive scale. We hope you've got a lot out of it and some ideas on how you can use Ansible in your large-scale environments. Thank you.